Okay, so welcome to the afternoon tutorial session. People are still filtering in, so please sit down quickly. The session is entitled Geometric Deep Learning on Graphs and Manifolds, and it's going to be presented by Michael Bronstein, Johan Bruna, and Arthur Shalom. And I'll just hand it over right away, and thanks for being here.
Okay. Hello? Hear me? Okay. Hello, welcome everyone to our tutorial. So we are going to talk during the next 2 hours about geometric deep learning on graphs and manifolds. So what is geometric deep learning? So it starts, as many deep learning stories, with very good numerical results. And as you all here all know, I don't need to convince you, we have seen many success stories, many successful applications of deep learning on all sorts of tasks, but all involving data that might be text, speech, or images or videos. And in many of these instances, there's one common denominator that in a sense is responsible for many of these successes. That is, these are architecture that we call and we refer as CNN, the convolutional neural network. So, but in the world, there are things beyond images, speech, or text. For example, you might be interested in trying to leverage some information on your social network, or you might be working on biostatistics or computer graphics, etc. And so in these domains, the questions that we are going to motivate this tutorial are the following. So what makes images, speech, and text, what kind of geometric structure makes convolutional neural networks successful in these domains? And how can we, if we understand some intrinsic or some universal properties on that makes convolutional neural networks successful, how can we leverage this information on domains that are non-Euclidean? So what is a non-Euclidean domain? So in this tutorial, we are going to focus and we are going to keep in mind these two very simple setups. One is a manifold that you can imagine as a shape in a three-dimensional space that has, let's say, a two-dimensional topology, or a general graph. And we'll see many examples in the tutorial of many situations where these two data structures arise. So what are the different tasks that we are going to be considering and that are treated in our framework? So the first one is to make this distinction between what we call domain structure and data non-domain. Okay, so domain structure might be assuming like your favorite social network. So in a domain structure problem, you might be interested in using the graph or basically the connectivity as the input itself. And you might want to be inferring properties of this connectivity structure. As opposed to the setting where you might have a domain, like the same neural network, but now on top of this domain, you might be observing or measuring signals that, for example, the age or the preferences of users, etc., etc., etc. So you might be interested in understanding or processing functions on this domain. We might also think about the setup where the domain is either fixed. For example, in a social network, again, you might have the same social network but different functions that you observe on this network. Or you might have problems where the domain itself is going to be changing from one instance to the other. For example, if you want to be able to do shape correspondence, you have to every new data point is going to correspond to a new graph or a new manifold. We also are going to be making the difference between the setups where the graph or the manifold structure is known, is measured by the sensing process, and also problems where this geometric structure that we presume is there is not observed. For example, you might imagine having a point cloud of particles in particle physics, and these particles are measured in some space, and you know that they might be interacting in a certain way, but you don't know a priori what is the geometrical structure on this data. What are the tasks that we might be interested in solving? So there can be tasks that, similarly as in image classification, that take as input a whole graph or a function on a graph and try to output some categorical variable. For example, the type of the molecule, or whether this molecule is from category A or B. We might also be interested in problems where every node or every edge in this graph has some label that we want to infer. For example, we might be interested in solving community detection problems, okay, inferring the voting preferences of people. Similarly, as in computer vision, we find these examples as, for example, in image segmentation, right, where the goal is to every pixel in the input will be associated a label. Okay, so what is, with this motivation, what are we going to describe, or what we are going to explain in this tutorial? So first, the story starts with convolutional neural networks in their natural domain, which is the Euclidean inputs. And then we are going to try to see slowly how, by introducing a little bit of graph theory and a little bit of Fourier analysis, we can generalize this construction to different domains. And we will see mostly two different routes for that. One is based on the spectral domain, and the other one are spatial domain. And we are going to conclude the tutorial with hopefully broad range of applications that I hope will illustrate why this story is interesting for you. Okay, so as I said, I mean, with this audience, I don't need to spend precious time describing what convolutional neural networks are. So I thought that maybe we can just start by describing all the good things that they have. So as you know, convolutional neural networks, they are convolutional, right? And convolutional here is motivated or is justified by the fact that the images, the inputs that we need to treat, have some statistical property that is translation invariant. In statistics, this is called like stationarity. The other interesting and key property that we will see later, why is it so important, is this idea that a convolutional neural network, as we have heard many times before, has this ability to break the learning problem into different scales, right? So basically the role of the first layer is just to figure out a way to map images that have a certain size to images that are slower, that are of lower resolution. So this idea that the learning can be broken into different steps, that corresponds to this notion that some of the tasks that we care about, they can be learned by learning in step by step, by this notion of compositionality. Another property that is very important, and we'll see also later, is that not only these models are convolutional, in many successful instances, these filters are localized in space. And the intuition behind why the filters have to be localized in space can also be understood from the geometrical point of view. This idea that if I applied my filters to an input that is slightly deformed, many of the filter responses are going to be stable if the filters are local. And the first and the third property together also give us this bonus that the number of parameters that we need to learn per layer is constant, right? It's a constant that does not depend on the dimensionality of the input. Another interesting and key property of convolutional neural networks is that they can be computed quite efficiently, especially now with the GPU architectures. We just pay a linear time, right? And by basically grouping all these properties together, what it means is that because we are breaking the estimation in different scales, and every estimation step, every layer, we just pay a constant price of parameters, what it means is that the overall learning complexity of this model scales very nicely with the dimension, right? So it's not exposed to the course of dimensionalities of other models. And so what is the geometric, what are the assumptions, the underlying mathematical structures that are underpinning this construction? So we can define convolutional networks either in a Euclidean domain or in a grid, in a discretized version on a grid. And these domains, they have two crucial properties that make this construction possible. So the first one is, as you may know, that this domain, this grid, you can translate it and you get basically the same copy, right? The grid has this built-in operator that is the translation. And it has another built-in structure that is the idea that I can take my grid and I can make it twice as coarse, right? I can make it twice as small and I get essentially the same copy of the grid. Okay, so this idea that you have this very nice domain with these two properties also plays very well with what I said before, right? That with this structure matched with the right statistical properties of images make the whole story work very well together. And so the roadmap that we're going to follow is to extend this construction to more general geometries by trying to replace or trying to come up with the appropriate definition of these two operations, right? What does it mean to filter, and what does it mean to pool in more general domains? And as I said, there are two different routes to address this question. The first one is to work in what we call the spectral domain, and we're going to see what this means precisely. And the other route is to work on what we call the spatial domain. Okay, so let's go non-Euclidean. So as I said, let's keep these as two prototypes of the images that we are going to, the inputs that we're going to process, so manifolds and graphs. And so the challenges that we need to address for this construction are basically we have to assume that the same stationarity properties are going to hopefully hold in the tasks that we are going to be using these models for. And what we need to solve, as I said before, is what does it mean to filter so that we can leverage this weight sharing of convolutional neural networks across different parts of the domain, and how can we define the compositionality? How can we pool the information in this domain? All right. So, in 1 minute, what are the minimum machinery that we need to know and to learn before we can do that? So, what is a graph? So, a graph, in our context, for us, it's just going to be a set of nodes, vertices from 1 to n, that are connected through some grid, like some edge structure, right? So, this edge structure can be just basically relying vertices one to the other. And we are going to assume here that the graph is undirected, which means that there's no preferred directionality in the edges, and that every edge has a positive weight associated with that. So I said before, in a graph, we can define functions. So there's here like a little example that shows a simple function on this graph that at this point you can just think about this function as a vector, right? It's just a vector of n numbers that encode the value of the function at every node. And these functions are actually we can think of them as being elements of a Hilbert space. In that case, a very simple Hilbert space with a standard dot product. And this function in this functional space, as I said, we are going to be exploiting or using some geometry. So in order to define geometry, you need to be able to measure the smoothness of function or the regularity of things, right? So how can we measure regularity of functions like the one you see here? So this is achieved with a very popular, famous, historic operator that is called the Laplacian. Okay, so the Laplacian is just an operator that is linear, that is going to map a given function f into the Laplacian of f, which is essentially the difference between the function and its local average. Okay, so just you look at the function, you take a weighted average at every node using the weights of the neighbors, and then you remove the average. All right? And so in matrix form, you can look at this Laplacian as the difference between two simple matrices, what we call the degree matrix, that is diagonal, and the weight matrix, that is the input, like it's how we encode the graph. In that case, it's symmetric because the graph is undirected. Okay, so as I said, this is a tool that we want to use to measure the regularity of functions. So how can we measure the smoothness of a function? So this is something that we do with what we call the Dirichlet energy, which is essentially the weighted average, so we look at the differences between the function and its at every node and its neighbors, and we look at the square difference, and we weight by the weighted sum according to the weight of every edge. And so this can be written as a function of the Laplacian as a quadratic form. Okay, so like a f transpose, the Laplacian times f. So this is our tool to measure the smoothness. So this construction, it turns out that we can perfectly mimic it, or we can follow it exactly by replacing the graph with a Riemannian manifold. So what is a Riemannian manifold? So the intuition is a manifold is just going to be like a twisted Euclidean plane that it's living somewhere in a higher dimension Euclidean space. So technically, formally, what it is, it's a topological space where every point has a kind of a copy of an Euclidean space that we call the tangent plane. And in this tangent plane, we have a metric, like basically we have a dot product that is characterized by a metric tensor that is itself continuous. And again, similar as before, we can define in this manifold, either we can define scalar fields, which are just functions defined on the manifold, and we can define also vector fields, which are functions on the tangent bundle. And both of these functional spaces, they come with their nice, well-behaved metrics that make them into Hilbert spaces. And so as before, we can measure smoothness in this world, in this manifold, by using the Laplacian. In that case, it's called the Laplace-Beltrami operator, which is constructed a little bit more using a divergence and gradient, but this doesn't really matter. So it has, again, the same properties as before. It's a symmetric, it's a self-adjoint operator. And you can think about this Laplacian as being basically the continuous limit of a discretized, a manifold that is appropriately discretized using meshes. So again, we have the Dirichlet energy as before. Okay, so once we have this Dirichlet energy, we can use this energy to basically try to think about the functions and organize function in terms of their smoothness, right? It would be good to understand what are the classes of functions that are very smooth, what are the classes of functions that are less and less smooth. And so the right way to measure this is to consider basically a basis, like a linear representation of functions, where every basis element encodes a certain class of smoothness, right? And so we can encode this, we can measure this by solving the following problem. It's a constraint optimization problem, right? We're going to look for what is the function that is the most smooth, so that minimizes the Dirichlet energy, that is the unit norm. That would be the first setup, the first line. The second line is, okay, what is the next basis element that is orthogonal to the first one, that is as smooth as possible? And so it's not surprise that this problem can be written in a much more compact and maybe familiar form as an eigenvalue problem, right? You want to find a basis that minimizes the trace norm of, well, that corresponds to the eigendecomposition of the Laplacian. Okay, so the Laplacian eigenvectors are the solutions. They encode us. They give us basically the dictionary to understand smoothness in graphs or manifolds. Okay, and so what does this eigendecomposition give us? On the one hand, we have these eigenvectors that are orthogonal, so unit norm and decorrelate like orthogonal one to each other. And then we have associated a family of eigenvalues that are non-negative because the Laplacian is positive semi-definite, that encode basically the smoothness class of every one of these basis elements. And so probably you are familiar. If you try to solve this problem in an Euclidean domain, you will get something that it looks very familiar, right? So here you get the sine and cosines, right? Which are, as you might imagine, basically the solutions, or they encode, they measure smoothness in a global form, as the Laplacian conveys. So if we do the same thing on a general graph, we get that sort of functions, right? That basically encode different smoothness. So as we increase the size of the index of the eigenvector, we get things that are more and more oscillating. And the same thing on a manifold. Okay. So, as you might have suspected, or at least part of the audience have suspected, this looks very familiar. This looks like Fourier, right? So indeed, Fourier is intimately related to the solution of the Dirichlet energy. And so, just to refresh a little bit, the calculus, the harmonic analysis concept. So what is a Fourier transform, or what is the Fourier analysis? Is a way to think about the function f as a sum of sines and cosines. Okay? And so what are the coefficients that I need to use at every frequency? They are precisely basically the decomposition and the basis. So this is just taking a vector, like thinking about the function as an infinite dimensional vector, and expressing this vector in the Fourier basis. And so it turns out that one way where we can intrinsically define this Fourier basis is, again, from the Laplacian. Okay, so as I said before, the solutions of this wave equation, so basically looking at functions that are eigenvectors of the Laplacian gives us, no surprise, the atoms of the Fourier representation. So now that we have this way to characterize Fourier as solutions eigendecomposition of Laplacian, and we have the Laplacian in these domains, we can perfectly we can take the concept and transfer it to the graph and manifolds. So this gives us very automatically a representation of functions in graphs and manifolds in terms of their Fourier coefficients. So how we do that, we take a function f and we project it over the basis that diagonalizes the Laplacian, and this gives us coefficients f hat k that allow us to reconstruct. And these are precisely the eigenfunctions of the Laplacian. Okay, so here you see again another example where this, what does this decomposition look like? Okay, so in getting closer to our objective of mapping these things to convolution neural networks, you might also remember and suspect that this basis decomposition, this representation in terms of Fourier, must have something to do with the convolution, with filtering. So indeed, let's just verify that this is the case. If just refreshing the definition, a convolution is just the convolution between a function and a filter. It's a linear combination of the function with the translated versions of the filter, and because by definition we have the convolution commutes with translation, right? Basically, translating before or after the convolution yields the same result. And so, because of this property, what we have is that the Fourier transform, this convolution operation, is expressed as a diagonal operation in the Fourier domain. So what does it mean? It means that if I look at the Fourier transform of the convolution between these two functions, this is just a pointwise operation in the frequency domain. And in many situations, this is in fact the way convolutions are computed, right? Because we can leverage the fact that we can compute Fourier transforms very efficiently in an Euclidean domain. So in the discrete case, what does this look like? So as I said, the convolution is just a linear operation. So you can just look at the convolution as a matrix vector multiplication. And so this matrix has a very special structure, right? And this is called a circulant structure, because every row of this matrix is just a shifted version of each other. And so because of this special structure of this matrix is the diagonal in the Fourier basis. What does it mean? It means that we can write it as basically the Fourier transform times the diagonal matrix of G hat in the diagonal times the Fourier transform inverse. And so again, we verify that this is equivalent to writing the convolution as an operation that is diagonal in the Fourier domain. And so similarly as before, we can take this analogy, this convolutional theorem, as a roadmap, as a guide to think about convolutions in a more general domain, right? Because what we have just said is that we have expressed the convolution as a very specific operation in the spectrum of the Laplacian, right? Something that is diagonal in the Fourier domain, in the eigenvectors of the Laplacian. So we can use this as a definition, as a tool to think about convolutions in this general domain. So what we are going to do is that we are going to take the Fourier coefficients of the filter, the Fourier coefficient of our function, and then just multiply each frequency independently, and then use the inverse Fourier transform again. Right? So in matrix vector notation, this corresponds to basically, as I said before, right? So taking the function f, going in the Fourier domain, multiplying every frequency independently, and then going back. So this looks all nice and simple, but of course it's not as nice as the reality is not as nice as in the Euclidean domain, right? Because this function, this matrix G, now is not as beautiful as in the Euclidean domain because it doesn't have this circulant structure, right? And this is something that connects to what I said at the beginning, right? That in general graph, it doesn't mean anything to translate, right? The domain is not the same. It does not have the operation of translation in general, right? It's only in very specific domains, very specific graphs, that this operation makes sense. And the other thing that is, and the other thing, of course, that I should mention is that the coefficients of this filter, of course, they depend on the basis, right? They depend on every graph will have a different set of coefficients. And so this representation, what I have to say is that it comes with some limitations that we are going to see just right in a second, how these things can be overcome. But I just wanted to illustrate this with a very simple example. So this is a simple function over a domain, and we can try to understand how this spectral decomposition varies or is stable as we make little changes in the domain, right? As the horse is going to move, let's see how things are going to behave. Okay, so here we have a very specific, filter in this domain. So as now we are going to change the domain, as you see here, the notion of the filter that we defined in our initial domain, as we deform the horse, completely changes sense, right? So here what we are seeing is that there's an important limitation of thinking about convolutions in the Fourier domain without localizing in space that needs to be addressed. And so this is another example of a high-frequency filter that we see that how it's not stable as we deform the domain. So with that, now we are going to see how this technology can be used to learn. And I will let Michael now continue. So thank you.
Thank you very much, Joan. So thank you for this introduction. So now we know what is meant by Fourier transform on a non-Euclidean domain, whether it's a manifold and a graph. Let's now dive deeper into how to use this construction to do convolutional neural networks. And basically we need two basic building blocks to construct a CNN. We need a convolution, right, or some kind of notion of filtering on our domain. And we also need pooling. So this is what I am going to describe in the next about 20 or 30 minutes. Okay, so the very simple ideas we've seen before, basically we can just apply the filtering as a diagonal operation in the frequency domain. So that's exactly what we see here. Basically, we are given some signal, a function f, right? We compute its Fourier transform and then multiply by a learnable diagonal matrix of weights. Basically, these are the spectral coefficients of the filter. Then we compute the inverse Fourier transform, and this is what replaces the standard Euclidean convolution on a graph or on a manifold. And we can do with this convolution the usual things that we do in convolutional neural networks, right? We can apply nonlinearity, for example, half rectifiers that are very popular. We can have multiple layers of such operations, and so on and so forth. So basically, this very simple idea yet comes with several severe disadvantages. First of all, what Joan already mentioned, that the filtering operation is domain dependent. So if we have especially in strong non-isometric deformations of the domain, the result will change quite dramatically. The second problem, which is different from the classical case, in this formulation, the number of parameters, basically the number of spectral coefficients of the filter is order of n. Basically, it depends linearly on the size of the input. And this is, of course, very different from the order 1 that we want to achieve in analogy to the classical CNNs. The other thing is that, unlike the Euclidean case, where we have efficient ways of computing the fast Fourier transform with n log n operations, usually on general graphs, it takes order of n squared. So the computation of the Fourier transform is inefficient on general graphs. We don't usually have f of t on non-Euclidean domains. And the third thing, one of the actually powerful features of convolutional neural networks is that the filters that are used in CNNs are localized. And here, because we are given a freedom to choose any spectral multiplier, nothing in the world guarantees that in the spatial domain such filters will be local. Okay? So let's address these problems starting from the last one and going to the first one. And basically, the property of the Fourier transform in the Euclidean domain that also generalizes to the non-Euclidean setting is what sometimes is called in signal processing literature the vanishing moments. Basically, if we look at the moment of a function in the spatial domain, it translates to the integral over a high-order derivative of its Fourier transform. And basically, if we want localization in the spatial domain, we want higher-order moments to be small or even vanish. It means that higher-order derivatives of the Fourier transform must also vanish, meaning that the Fourier transform must be smooth. It must be a smooth function, where we understand frequency as the eigenvalue. Okay, and basically the idea here is that we can parameterize the filter as a smooth spectral transfer function. Basically, if again we regard the eigenvalues of the Laplacian as frequencies, we want to apply to them some smooth function. And the application of this function to the Laplacian is understood in the sense that we perform the eigendecomposition of the Laplacian and apply this function element-wise to its eigenvalues. So basically we have here a diagonal matrix of tau, the spectral transfer function, applied to the individual eigenvalues. Okay, and here we can parameterize this function by a small number of parameters. We'll see particular examples for polynomials. And the number of parameters can be, basically it's under our control. We can make it independent on the input size. So this will be order of 1. Okay, and let me show you, here is an example of frequency response that is not very smooth. And you can see that the result is very delocalized in the spatial domain. And you can also see that it's unstable. It's similar to the example that Joan showed before. This is an example of a smoother filter that is way better localized in space, and also it turns out to be much more stable. So in general, local filters, when they're computed in the spectral domain, tend to be much stabler than global. Okay, so as I mentioned, we can basically it's our choice to define this smooth transfer function. A particularly convenient choice is a polynomial, or to be more precise, a Chebyshev polynomial. Basically, that's an orthogonal family of polynomials, and we can apply when we apply to the Laplacian, we can basically write it as sum of powers of the Laplacian. As a result, we get first of all fixed number of parameters per layer. Right, these are coefficients of the polynomials. Basically, they parameterize our spectral transfer function. The filters are also localized, and they are guaranteed to have R-hope support. And that's because the Laplacian is a local operator. Basically, application of a Laplacian to a function on the graph affects only its direct neighbors. So if we apply an R's power of the Laplacian, we affect only neighbors of neighbors removed R times. Right? So basically, we get guaranteed local filters. We also don't need to explicitly compute the eigenvectors and the eigenvalues of the Laplacian. Basically, we can apply this function to the Laplacian itself by just taking powers of the Laplacian. So there is no expensive eigendecomposition of the Laplacian. So there is no expensive explicit computation of the Fourier transform. And if our graph is sparsely connected, meaning that the Laplacian contains only order of n non-zeros in each row and column, basically the cost of this operation is order of n. Okay? So let me show you an example. What you see here is an example of a graph. Basically, it's a citation network. Each vertex represents a paper, and edges represent citations. So we assume it to be undirected for simplicity. And each paper is described by some feature vector representing its content. And the task here is to classify each of the papers into some field where it was published. So this is a classical data set that is used in network science and in graph theory. And some of the state-of-the-art methods, their results are summarized here. So this is called the core data set. And the best methods achieve something like 75% of accuracy. And these methods do not use any context information, so they consider each vertex individually. If you apply convolutional neural network on graph, you get significant improvement in performance above 80%. So this is just maybe a toy example of an application of a graph convolutional neural networks. So some interesting data set. So we talked about convolution. Let's say a few words about pooling. So basically, in the Euclidean case, pooling corresponds to changing the resolution of our grid, right? Basically, we for example, usually downsample an image by a certain factor and take some operation like maximum. So the same thing can be done on graph. In this case, the reduction of the graph resolution can be done by a graph coarsening process. For example, when a pair of vertices is collapsed into a single vertex, and we can take an operation like maximum or average on this pair. So we have an operator that transfers data or functions from the finer graph to a coarser one. And basically, if we arrange the vertices in a particular order in a tree structure, this operation can be done as efficiently as the Euclidean counterpart. Okay, so to summarize the limitations of spectral methods, of course, their advantages are very clear because they have direct interpretation using the standard classical signal processing intuition. But the several limitations that they come with is, first of all, as we already mentioned and shown in several examples, it's poor generalization across different domains, especially when the domains are strongly non-isometric, unless the kernels are very localized. So I should mention that there is a recent work that tries to somehow remedy this problem using the idea of transformer networks applied in the spectral domain, basically trying to align the bases in the way that the Fourier coefficients in different bases speak in the same language, so to say. Another problem is that basically in the Euclidean case, the Laplacian is rotation invariant. So basically the kernels that we get with this Laplacian are symmetric. They look like this. So that would be, for example, a polynomial kernel when the Laplacian is taken from the Euclidean grid. And there are ways of constructing anisotropic kernels, but this is more difficult to do on general graphs. You can do it on manifolds when you have some underlying low-dimensional structure, basically the tangent space. So we'll mention it in the following, but on general graphs, this is quite a big challenge. And finally, the underlying assumption was that the Laplacian matrix is a symmetric matrix. This is what allowed us to have orthogonal eigenvectors and real eigenvalues. So basically, dealing with directed graphs with spectral methods is challenging. There are some generalizations of these constructions, but it's not straightforward. So the frameworks that will be presented next approach this construction from a different perspective, basically using a spatial domain formulation of filtering. Okay, and I will pass here the stage to Arthur, who will talk about the graph neural networks.
Okay, so we talked about the kind of spectral, the Fourier side constructions, and now we're going to try and talk about the spatial side constructions. These, in some sense, are simpler to write down. They require less theory to write down, but that theory is useful for understanding even the kind of spatial side constructions. So the very last few constructions that were talked about actually can transfer between graphs, but it takes a little bit of work to make that happen. In some sense, the nice thing about the spatial constructions is that they are automatic. It's automatic to feed it a graph. So the spatial side constructions are designed to input a graph and a function from the nodes to RD. So these kinds of constructions are actually quite old. They're older than a lot of the stuff we've talked about, but people had forgotten, as has happened. So Gori, Muffardini, and Scarcelli had the graph neural network construction in 2005. It's actually a very general paper that foresees a lot of later things that we decided were important. Okay, so it turns out that in order to understand what to do with a graph on the space side, the best thing to do is understand the simplest thing to do is to understand what I should do to input a set. The thing about graphs is that they are permutation invariant, and the thing about graphs is that they can be different sizes. And those, once you have kind of an understanding of how to deal with those two things, you can actually do all the things you want to do. So sets happen to be invariant to permutations, and sets, if you want to have a neural network that eats a set, it has to be able to do dynamic resizing. So let's tackle this first. Okay, so the simplest thing, if someone says, okay, give me some operator that if you give me a set of vectors, it's permutation invariant with respect to the set of vectors, and it is it's invariant with respect to the size of the set, is taking a mean. So taking a mean is a really nice thing to do. If people who do, bags of things are kind of the classical approach to, if you have a problem, the very first thing you should do is take a bag of things, because it's often really good. Of course, taking a sum is not the only thing you can do. You can take products. More recently, people have started doing attention. Attention is a thing which is dynamically resizable and invariant to permutations. In the things that follow, we'll talk a little bit about, we're going to talk more about sums and a little bit about multiplicative things, about geometric means. Attention, less so. And what it turns out is you can think of, actually it turns out that attention or multi-hop attention is another way of processing sets or processing graphs even, but it's a sequential way of doing it. Multi-hop attention looks at a piece of the graph or a piece of the set and then does a little bit of processing, looks at a different piece, does a little bit of processing, so on and so forth. Whereas graph neural networks and graph convolutional networks work in a distributed or parallel fashion. And we'll see how this looks. So actually, we could have a complete branch of this talk where we talk about multi-hop attention as graph neural networks. It feels a little different. And we won't do that. But actually, multi-hop attention does work on graphs as well, and works on sets as well. But okay, so we're going to find a graph NN type approach, or a mean-based approach that works on sets. So how does it work? Let's suppose someone gives you a set of m vectors. What we're going to do is we're going to pick two matrices. We'll call them H and C. And H is the matrix that you're going to apply to yourself. And C is the matrix you're going to apply to everybody else. So let's go through the notation in this slide. If you'll notice, there's a bunch of superscripts. So each vector H has a superscript. That's going to be, the superscript tells you what layer of the network you're in. So for example, H super naught is the set of vectors in the input to the network. There's a bunch of subscripts here. The subscripts correspond to which vector you're talking about in the set. So H1 naught is the input, is the first element of the set, and it's at the input level. H1 super 1 would be the first element of the set after one application of the network, or in the second layer. So how can we process a set like this? Well, we do some nonlinear function of the H matrix applying to yourself, and the C matrix applying to everybody else. Now, what is everybody else? Yeah, you can see the hand. Everybody else is the mean of everybody that's not you. So again, we know a mean is permutation invariant, and we know a mean is scale-free. So that's great. This thing, you do something to yourself, and you do something to everybody else. And because you just work on these two classes, you're permutation invariant and scale-free. And so, okay, these equations look a little bit forbidding. Let's look at it as a picture. I know some people like it much better to have a picture. So you input yourself and everybody else. And what is everybody else? Everybody else, that's this red stuff, is the sum of everybody that's not you, or the mean, sorry, not the sum, of everybody that's not you. And you have yourself, and you feed that into some small some neural network, and that gives you an output, which is the kind of what sits over the set, the vector that sits over that set element at the next level. Let's look at the same thing. This is, again, exactly the same thing, but now written in matrix form. So we've seen this 3 times. I really want to get this idea across, because this is the idea for a graph NN. Here it was kind of element by element. Here it was in a picture. And here it is in matrix notation. If we set C bar to be the matrix C, and again, super I refers to which layer. So C bar is just C times divided by the number of elements in the set. Then if we write what we had before, we just have a plain multi-layer neural network, but with a matrix that has this form. On the diagonal, it has these, it's block diagonal with these H blocks on the diagonal, and it's on the off diagonal, it has these C bar blocks. And when you apply this thing, you apply it to the concatenation of all the vectors. And you can see from the shape of this matrix, it's permutation invariant. And you can see from this that it is scale invariant. And so you have a really cool object here already, like independent of graphs or geometry or anything else. You have an object that, you have a kind of construction that you can parameterize something that eats sets. And it eats sets of vectors and processes them as sets of vectors. And as we talked about before, it does it in parallel. So here it does all the operations in parallel, and then it takes the mean of everybody communicates with each other, and so on and so forth. So let's see what this looks like. Is this video going to play? Okay, I'm going to give up on the videos. Oh, something happened. Okay, I'll give up on the videos. So what you would see, if this thing was working, what you would see in the video is a bunch of cars in an intersection going through. And again, the cool thing about this sort of construction is that it doesn't care how many objects are in your set. So you can train one neural network and it dynamically resizes on input. So at moment 1, you can have a swarm of objects, and at moment 1, somebody leaves the swarm, and somebody else comes in, and somebody else leaves, and somebody else comes in. And at all times, you're still processing that object with the same neural network. Okay, so that's what we do with sets. The graph neural network is the same thing. We don't change a single thing, except now, instead of taking a mean over everybody, you just take a mean over your neighbors. So here, again, we're going to have a function, h0, from the vertices of the graph to RD. And we're going to perform the updates just like before. The h at the next layer, at the position j, is given by some function of the current hidden state at that location and everybody else's activation. And everybody else's activation is now, instead of just going to be a mean, it's going to be a mean weighted by the graph weights. Okay? And here I'm just, for simplicity, going to assume W is a row normalized matrix, just for simplicity. I don't want to write too much stuff. So the only difference between the thing before that we did on sets and the thing that we're doing now on graphs is that you take the means over your neighbors, right? And this is the simplest form of graph NN. And it's actually reasonably effective already for lots of fun things. That was supposed to be another video, which I can't show you. It's the GraphNN version of this. Okay, so now let's go back to what those guys were saying before about the spectral networks. So what we know from the spectral theorem is that taking powers of the Laplacian, or in this case powers of the diffusion operator, this is this W, is the same thing. You can take a function of the spectrum, or you can take a function of the actual operator. It doesn't matter. That's what the spectral theorem says. So it turns out that if instead of just having f of W times h here, you have f of W times h, and then, so this was just h, so W to the 0 power of h is just h. And then you have W1, well, this is the thing we had before. And then you can put higher powers in too, you recover something that looks very much like the spectral construction that we had before. In fact, it's exactly the same thing as the spectral construction that we had before. It's just you've built it on the space side. And a lot of the things that were talked about before, when you do this kind of small polynomial thing with that's localized in frequency, you only have a fixed number of hops. Well, here you can see it explicitly. If we build this construction on the space side, we only have that many hops. So when we do it this way, again, you can really see, the graph is dynamic at test time, because the output of a layer is a function of the graph and of the input, right? And so this is nice. It really, you can eat the graph at test time. Okay, there's one thing I want to say about that. So because this is implemented spatially, we can take the graph as an input. But actually, there's a bit of a lie, and there has to be, because the pictures they showed you before, the videos they showed you before, said, you can't actually take a graph as an input because the thing is not stable with respect to perturbations of the graph. And what happens is, the higher the power you use here, the bigger the R is, the more powerful the method is, the more rich kinds of filters you can build. But the richer, there's a trade-off. The richer I'm allowed to make my filter class, the more dependent I am of the exact graph structure I have. And for example, let's imagine a really simple thing. Let's imagine a chain of vertices, a really simple graph. If I connect the last two, the topology completely changes. And if I look at the weight matrix, which is just one hop, I can't see that change in topology at all. But if I look at W to the number of nodes, all of a sudden I can see that change of topology as I go around. A small change in topology, I just make one edge, all of a sudden w to the 50th power, if I had 50 nodes, means something completely different. And so you have this trade-off between having very rich filters as you increase the power here, and having filters being able to honestly eat the graph at test time. Okay, so I have this. I'm just going to say a few things. This was kind of the most simple construction here. You can do all sorts of bells and whistles to kind of make it more flexible. So for example, you can decorate the edges, so you don't have to have just one edge type. You can have lots of edges. Another way of thinking about that is having multiple graphs. And so your update equations would look like this. You can decorate the vertices. So if I want to say something, if everything up to now has been completely permutation invariant, but maybe I want to give some information about some of the vertices. I can tell you that this vertex is of type A and this other vertex is of type B, right? So I can mask out some of the relationships. Again, this is an easy thing to do. Now, if you really want to push this all the way, so here we have kind of vertex decoration, you can push it even further. You can make the graph weights be something which is learnable. So you can make the graph weights be a function of the current hidden states. So a really simple thing is to do, that should be a minus, whatever. But you can do a really simple thing where you kind of have some sort of, say, local gating that say, well, if my hidden states are very close, then I'm going to compare them when I take the mean. Otherwise, I'm not. This construction is essentially what is called an interaction network or neural message passaging, and it's actually super powerful. And I think actually this starts to be somewhat different than a COMNet. This starts to feel different. At least normally when we build COMNets, we don't have multiplicative interactions. Our COMNets are usually of the form filter, nonlinearity, perhaps some pooling, filter nonlinearity, perhaps some pooling, filter nonlinearity, so on and so forth. We don't usually in our COMNets have multiplicative interactions or attention or gating, things like this. You could do it, and then it would look like this. So this is in some sense, once you start to get to this interaction network business, it starts to look less like a COMNet on a graph and starts to look a little bit different. We could build COMNets on the grid like that, but we don't usually. Okay, and there's all sorts of other things you can do. You can have, even though you don't have kind of this attention type multiplicative interaction, you can have multiplicative interactions on the way your own response and everybody else's response comes in. You can have W that depends on layers. You can have all sorts of skip connections and all the normal things. But the point is, the space-side constructions allow you to do all the things that you're used to and work pretty well. So I want to talk a little bit more about something that Michael mentioned at the end of his section, which is, well, what if we take this construction, this GNN construction that we've just described, and say, well, let's say, what does that look like back on the Euclidean grid? Everything we said worked on a graph. What if we go back to the grid? What does it look like? Well, if the graph is a regular lattice, then as Michael said, you can only get isotropic filters. I mean, if you think about it, everything here, let me go back, even with high powers, everything here was just powers of an isotropic matrix, right, on the grid. So everything is going to continue to be isotropic. So if you have a single isotropic weight matrix, then a graph in N gives you radial kernels, and that's it. And if you think about it, that's a pretty huge change. If you have a COMNet can have edge detectors, and a COMNet can have all sorts of things that really detect orientation. So why is it that this GNN construction, which looks kind of similar in a lot of ways, why is it so much less expressive? And of course, the answer is there's no notion of up and down on a graph. This is, to some extent, if you want an intrinsic solution, there's no way you could, on a graph, get edge detectors, because there's no notion of up and down. So up and down on the grid come from the group structure. One of the generators of the group tells you which way up. The negative of that generator is down. The other generator of the group tells you which way is right, and the negative of that is left. Right? Because the grid has this special structure that a graph doesn't have. More than that, it's actually implicit in the ordering of the. It's implicit in the coordinates of the representation of the filters. So because at every location on the graph, every location on the grid, if I look at the way the filter touches it, this always touches the top left, this touches the middle left, this touches the top right, this touches the left, this touches the middle, and so on and so forth. That order is the same order everywhere on the graph. And again, this is, in some sense, something that comes from the group structure of the grid. But that doesn't make sense on the graph. By the way, so one thing which is really cool and funny is that this goes backwards, actually, as well. If someone just gives you a pile of patches from images and doesn't tell you that they're patches from images, and in fact, they even permute all the indices, but they don't tell you, and they just give you this pile of things, you can immediately recover the correct ordering of the indices. And it's exactly, again, because of this permutation, because of this translation invariance that images have, and because there's local correlation between pixels. So if I were just to take the principal components of a set of patches, the first principal component, well, it'll just be the DC. But the second principal component will be either the variation in left and right, or up and down, and the third will be, up and down or left and right. So you can recover this. This goes both ways. But this doesn't happen on a non-regular graph. It doesn't happen on just some graph that someone's given you. The fact that you have the notion of orientation was really special on the grid, and you can't have it on a graph without adding some extra knowledge to it. But you can get edge filters back if you allow decorations. So a few slides back, we talked about vertex decoration. So if you do vertex decoration, then you can get, that's a simple way of getting edge filters back. There are other ways as well. You can use edge decorations, you can use vertex decorations, you can use other things as well. Michael will talk about something else. And in general, if you have extra information beyond the graph, you can actually give this to the construction. Okay, so I'll stop. Now, actually, we'll take a, how many minute break? What? Oh, we're going to have questions or break. Okay, so we're going to stop and take a break and do questions.
Okay, so before everybody wanders off, I do have an announcement, and that is that there was a change to the schedule. It's online, but I don't think it's in the program book, which is that the opening remarks are going to start at 5 o'clock, right here where you are now. So be sure to be here at 5 o'clock. So we're going to have questions now. So if everybody who wants to ask a question can line up at one of the mics, there's 2 mics by either of the projectors. So please do line up now. And while people who want to ask questions are coming up, I'm going to ask the first question. And that is, there was kind of let's say, a mention at the very beginning about how you can construct a graph or learn a graph. So if you think about like spectral clustering, very frequently what you'll take is Euclidean data or some other sort of data that you can embed in a metric space, but then you construct a graph on that data, and then you do some processing with that. So I'm wondering if you have any thoughts or comments about when you might want to construct a graph, when it would be useful to use a graph technique, and when you would say, no, we need to do some other type of thing.
When you would want to construct a graph from data points?
Yeah. So when you would want to construct a graph from data points versus when you might, and then apply some sort of graph techniques such as a graph convolutional network or whatever.
Yeah, so that's a very interesting question. So yeah, indeed. So if you have supervision from the spectral clustering, let's say that you know the labels or how you would like ideally your data to be separated, and you have some labels on how you know which are the clusters, then you can indeed like make this model learnable, such that several layers of graph convolutional network are going to be are going to produce clusters that match what you observe. So in that respect, yeah, there are some recent works that try to actually unroll spectral clustering as if it was a network, and then do backpropagation on it, and and directly learning the graph such that the resulting clusters are matching your data. I don't know if that was the question. Yeah.
All right. So it seems like we have more people on the stage left side. So let's start there.
Hey, hi. I have a question regarding graph convolution neural networks. So you mentioned in the early slides that you can use it for molecular classification or image classification. So I have a question regarding molecular classification, which you have graphs of different sizes and you have different Laplacian or adjacency matrices. And the assumption in the spectral convolution, graph convolution network is that you have the same Fourier basis, right? But for molecular classification, your graphs will have different Fourier bases. So how do you do molecular classification in that case?
Yeah, so
I have to apologize, but we didn't understand anything because of the echo. So can you repeat very slowly?
So my straight question is, how do you go for molecular classification in which graphs are of different sizes, and like how do you apply your graph convolution neural networks for molecular classification? Are you getting like what I'm trying to say?
So let me see if I understand. So the question is, how do you apply graph convolution neural networks to molecular classification where every molecule has different size?
Exactly. I mean, they might have different adjacency matrices. They might have different nodes. So can you apply it standardly, or how's it?
Yeah, so the entire last bit that I was talking about, all those constructions are completely happy to have every input have a different graph structure. That's in some sense the way they're designed.
So that is in spatial domain, right? Not in spectral domain.
So, but the thing is, if you think about, for example, the Chebnet that he was talking about, or if you kind of use higher powers of the weight operator, the higher the power, the more you can think of it as a spectral construction. Even though we did it in the spatial domain, it's acting on the spectrum in a way. And basically, if you use very high powers, you can't expect such a thing to work. So at some point, if the graphs are different enough, you're never going to be able to do this. You're never going to be able to compare them with a fully spectral construction. If the graphs are reasonably similar, then you can use more, higher and higher powers. You can use more and more of the spectrum.
Okay.
You can use, lower and lower frequencies. You can use less and less localized things. But for graphs that are, if you want one model to work on very different graphs, it's essentially going to have to be, unless you know something else special about it, it's going to have to be localized. Okay. And then you should build it in space.
Yep, makes sense. Thanks.
All right, so maybe we can go to the other side now.
Yeah, hi. Thanks for the presentation. It's very interesting. I have two questions. One is, what about directed graphs? It seems that construction could be extended easily if you change the neighborhood operation. And another question is about efficiency comparison. So you mentioned that if we take a regular lattice and label horizontal and vertical dimensions, we can recover spatial convolutional filters in image recognition. What will be the efficiency comparison in the implementation if we train a graph-based setup versus traditional convolutional network?
Sure. So directed graphs, well, the spectral methods, as we mentioned at the beginning, basically they are not made for directed graphs, but the graph neural networks can deal with directed graphs as well. So basically, that would be a short answer to your question. So you can deal with directed graphs with the graph neural networks. The second question about efficiency. So for example, if you take the spectral methods, the efficiency, basically, the cost of computing the filters is linear in the input size, under the assumption of sparse graph. And what is also important is that the Laplacian operator is local operator. And you can easily, at least in principle, parallelize it. Basically, each vertex, to compute the Laplacian of a function at a vertex, you just need to talk to your neighbors. So basically, you can compute the Laplacian at each vertex individually. You can do it in a distributed manner. There are actually computational frameworks that work with this kind of data, with graph structured data. Yeah.
Did you have any practical comparisons trying to do one way and another? Just out of curiosity.
So I don't think that basically the classical convolutional neural networks and the graph convolutional neural networks are comparable because obviously the domain of application is very different. you would probably not apply graph convolutional neural networks to images where you have regular grid structure and you can do the convolution operations in a way that is extremely well optimized with current hardware and software. But the classical CNNs cannot work on graphs, and basically the special methods that we discussed in this tutorial are actually built for this purpose. In terms of the order of complexity, it's linear. So that's basically that's the same thing. What is the constant? Of course, it will probably be higher. Yeah.
Thanks.
So I have a question. So how do you define spatial pooling on Riemannian manifolds? It seems like that kind of got swept underneath the rug, and there's a lot of variance in the way you might choose that operation.
Can you repeat?
How do you define spatial pooling in the continuous case on a Riemannian manifold?
So,
like on the horse.
maybe it's better if you answer. I mean, in general, if you have any multi-scale clustering of your space, whether your space is a continuous space or a discrete space, you can now define pooling, right? So there are plenty of methods for taking a manifold, especially if it's represented as a mesh or something like that, and cutting it into pieces at various levels of coarseness. And for example, especially as long as those are nested, you have a very classical notion of pooling. Even if they're not nested, you have a kind of very reasonable notion of pooling, right? You just need chunks of the space that are local.
Right, but that's then scale dependent on the chunks of the space, so you might be losing out on certain topological features. Right?
Could you repeat? I apologize.
So now you basically chuck it down to making a mesh of the right size on the manifold, then treating it like a graph essentially.
I see. So, well, okay. So when I'm going to give a very annoying answer, and I apologize for this, but eventually something's going to have to go on the computer, right? If you give me a description of your manifold as the level set of some function, I could actually write down for you the pooling the locations as that function of the zero set of something, right? I could give it back to you in the same way, in which case I wouldn't have this thing. But usually it's very rare that, to the extent you represent a manifold as a level set of something or something like that, then okay, I can give you the pools in the same form quite happily.
Okay. All right. That's enough.
Yeah, I have a question about the spatial convolution methods with respect to when we do have data that's in some sort of metric space that we talked about, like especially molecular data. So when we take an average over all of our neighbors, then we lose a lot of like structural and like sort of spatial information, right? When we are in some sort of like if we do have some sort of three-dimensional space. So how can we get around that problem?
So basically, if I understand the question correctly, basically in case of molecules, basically there is a lot of information that is carried by the intrinsic structure of the graph, right? Basically the metric structure, let's say the length of or the weight on the edges, but also on the configuration of points in 3D space. So in chemistry, at least I'm definitely not an expert, but if I remember something from my school chemistry, you have isomers. Basically you have molecules that have different configuration of atoms in space. But basically, the way that they are connected, the chemical bonds are exactly the same. So in this case, I think inevitably, if you want to take into account this information, you need to incorporate some notion of extrinsic information. Basically, for example, the XYZ positions of the vertices in space. Basically, using only intrinsic information, maybe in this case, gives you too much invariance.
But yeah. So what if we want to like have rotational invariance though, with respect to our molecule, and so.
So the intrinsic information, basically, if you use intrinsic structure of the graph, and this is basically all the methods that we described so far, you get rotation invariance automatically. But basically, you also lose, basically, you also get invariance to rotations, maybe some parts of the graph. So, for example, if you look at, I don't know, a molecule of sugar, then maybe you can rotate some of the parts of the molecule, and the structure of the graph will still be the same, but the chemical properties will be different. So current methods that look at only intrinsic information lose this kind of characterization of the molecule. So you need to account for extrinsic information as well.
Thank you.
Hi, I'd like to ask about auto-encoding with graph convolutions. So have you Could you briefly describe what a deconvolution and then an unpooling operation would look like?
Yes. So essentially, if you know how to do these operations in an image, then we have a dictionary where you can translate. So if the question is how do you do unpooling, well, there's always a mapping from the node at a certain resolution to the macro node, right? The pooling in a graph just amounts to coming up with associations between nodes, right? That define the larger node. So as long as you remember these associations on your way upwards, you can unpool by maybe copying the hidden state of the previous resolution up to the final resolution and then iterate there. Or you can do even more fancy things like linear interpolation if you have some way, like some form of an embedding.
Okay, thank you.
And I should mention that there are some recent papers that really develop these ideas now. So iClear submissions this year, there's a couple of papers that work on that direction.
Hi, thanks for the great talk. I have a question about the representative of the graph convolution, and the problem is as you mentioned, the graph convolution is isotropic. So, is there a way to define convolutional graph that naturally reduce to traditional convolutional neural network on grid image?
Yes, that's a very good question. So the answer is that yes, you can recover orientations in this formulation by just feeding the network a little bit of extrinsic information. So think about a graph convolutional neural network where the input to the graph are the coordinates of the grid. So basically every node you would feed maybe a pair of numbers that correspond to the coordinates in the original domain.
Yeah.
And the network then can basically you are giving the network an embedding, a global embedding that has global orientation. So then the network can figure out how to use this information maybe to learn oriented filters. And so if you do this experiment on CIFAR or on MNIST, you end up basically recovering orientation by just feeding input coordinates through the network.
Maybe if I can add to this question, so there are also some recent works that maybe this is what you meant. They basically they try to pull back a convolution from some domain with shift invariant structure. So, for example, if you think of manifolds with genus 0, basically that are topologically equivalent to a sphere, you can map them into some space, the sphere itself, for example, and you can pull back the convolution from there. So that's.
Yeah, thank you. And I also have a follow-up question about this. So in the talk we mentioned there are two ways to model the graph convolution. One is the spectral domain, one is the spatial domain. So what is the main advantage of doing this in the spectral domain? Because I think the general definition of the spectral convolution, for example, the Chebyshev net, can also be seen as a form of a spatial convolution.
So if you have a single graph that you're going to use for all time, right?
Yeah.
And in some sense, I don't think there's ever a good reason to do a pure spectral implementation,
yeah.
right? But if you have kind of a single graph that you're going to use for all your problems, all your data is functions from a single graph, then higher powers, and essentially that means that essentially you're doing something on the spectral side, even if you implement it a different way, that gives you a richer class of filters. So the more of the kind of higher powers of the weights you can use, the more rich your filters are. The trade-off comes when you have to decide how much of a new graph am I going to have to eat at test time. But if I'm going to have one graph for all time, then it's okay to use very high powers of the graph. Even if you implement it on the spatial side, you're going to use essentially a spectral construction.
Okay, yeah, thank you.
I'm afraid we're going to have to cut off the last question. If you can come in the subsequent question session, then we might have a chance for it. But we really need to start with the second half of the tutorial. Sorry. Okay, so with that, let's start with the second half. Thanks. Can someone from the AV team help with the projector? right, thank you.
Okay, so thank you very much for the questions. Let's continue now. So basically, we are now talking about, again, spatial domain methods for convolutional neural networks, but now from a slightly different perspective. Basically, what Arthur presented, the graph neural networks were a very generic method, and this is actually related to one of the questions that was asked during the break. So when you have some restriction of your problem, for example, when we'll be considering a manifold and not a general graph, then you also have more structure. So on manifolds, as was mentioned in the introduction, you also have a low-dimensional space at each point, the tangent space. And basically, you can work in this tangent space, you can create meaningful, so to say, charting structures, and that's exactly what I'm going to describe in this part of the tutorial. So basically, if we look at different ways of defining convolution, basically we can distinguish between the spatial and the spectral domain methods, right? And we've seen this classical definition of a convolution integral in the spatial domain, and the spectral domain definition using the notion of Fourier transform. So the easiest way of generalizing convolution was just to take what is a property in the Euclidean case, what is called the convolution theorem, and make it into a definition, right? We can define convolutional graphs or on manifolds as a product of the respective Fourier transforms, right? And we define in turn the Fourier transform as projection on the orthogonal eigenbasis of the Laplacian. So now we need to fill in the missing piece here, basically what could be. So the way that we can think of convolution or correlation for the purpose of the discussion doesn't really matter. In the classical Euclidean case on an image, basically you can think of it as the following operation. You take a patch of pixel, let's say square block of pixels around a point in an image, you multiply it by some template, you sum up the results, and you move to the next position, right? Basically you slide a window across your image. So we can try to do the same thing on a manifold, but the problem is that we don't have shift invariance. So when we move from one point to another point, the very way we extract this patch might change, right? Because of the non-Euclidean structure, because of the curvature of the manifold. So a way of thinking of these patches is actually we want at each point to attach some local system of coordinates in which we can parameterize these patches locally. So again, it's not a global system of coordinates. We still cannot do vector space operations with points on manifolds. We cannot add or subtract 2 points on our manifold or on our graph. But locally around a point, we might have this possibility. Okay? So on manifolds, it's actually very meaningful what kind of coordinates we can construct. For example, we can resort to a local geodesic polar system of coordinates. So if I think it's nicely illustrated in this image. So I take a point here on the surface of a man, the point X, okay, and I can measure geodesic radius from this point to some points in the neighborhood. This will be my radial coordinate. I can also measure the angle with respect to some orientation, to some chosen direction, and this will be my polar coordinate. So I will denote them by rho and theta. And we can define a set of weighting functions in this system of coordinates. So basically, what I want to do in images, basically to define a pitch, basically I want a weighting function that selects each pixel in my pitch, right? So I would like something similar on a manifold. It doesn't necessarily need to be a delta function that selects a single pixel. It could be something smoother. Okay? And then we can define spatial convolution as basically taking these, what we call pitch operators, so basically computing these local weighted averages of our function around a point. And this will give us basically j-dimensional set of numbers, right, that we can call a pitch by analogy to an image. We multiply it by the coefficients of our filter, right, our spatial template that we denote by g. And basically this is the definition of convolution in the spatial domain, right? So again here, because we work on a manifold, we have this meaningful notion of local coordinates. In particular, if we consider the spatial weighting functions as Gaussians with some parameters mu and sigma, right, the mean and the mean vector and the covariance matrix, we can actually write the pitch operator in this way. And if we exchange the order of summation and integration, what is written here is a Gaussian mixture. right? So basically, we can apply a Gaussian mixture to our function, and this describes the spatial definition of convolution. Okay, and we call this mixture model networks, or MONET for short. And if you look at the structure of these weighting functions that define our page operator, we can actually come up with different constructions. So actually previous models that try to do convolutional neural networks on manifolds used a fixed system of weights. For example, the geodesic CNNs used some weights that were defined basically some kind of radial and angular binning. The anisotropic convolutional neural networks that used anisotropic heat kernels of the operation used another set of weights. And actually you can learn the parameters of these Gaussians. You can introduce them as extra variables in your optimization problem when you do the training, and you can come up with basically an optimal page operator. Okay, so you can also apply this idea to general graphs. Now, on general graphs, you usually don't have a meaningful local system of coordinates, so you can use some graph theoretical features such as geodesic distance, degree, and so on, but these choices will be, to some extent, arbitrary. You can still, of course, define in this system of coordinates, or better say pseudo-coordinates, you can define some weighting functions, but basically, they will not have this nice low-dimensional interpretation as you have on manifolds. Okay, now you can actually show that with this construction you can generalize a lot of previous approaches, of course, including the classical convolutional neural networks, but also many other convolutional neural network architectures that were proposed for triangular meshes and general graphs. What is also nice, you can see the spectral methods, in particular the Chebyshev network, as a particular case of this page operator. So if you remember, in the spectral neural network, we had some parametric function of the operation applied to our signal f, right? In the spatial filter, we have a page operator that is applied to our function, right? And in particular, in the spectral filter, we considered polynomials of the operation. And you can easily see that basically these powers of the operation can be seen as a special selection of the weighting functions in the construction of our page operator. So basically you can obtain the spectral construction as a particular setting of this approach. Okay, so let me now give you some examples of how these methods can be applied to applications taken from computer graphics and 3D computer vision. And in particular, I would like to talk about actually one of the fundamental problems in these fields, namely the problem of shape correspondence. So basically this problem underlies a lot of applications, whether it's, for example, texture mapping, or applications like, for example, 3D avatars and so on and so forth. So basically our target is, given a pair of shapes, we want to associate different points on these shapes to tell whether they match or not. Okay, and we want these to be invariant, of course, to deformations, right? So we want, no matter in which pose the shape appears, we want still to be able to find a correspondence. So this is a motivation why we want to use intrinsic convolutional neural network architectures. Basically, we want, by construction, to make the architecture to be invariant to this set of degrees of freedom. In this way, for example, we don't need a lot of data where all the possible deformations appear, because by designing intrinsic architecture, we'll get these invariants automatically. And of course, we also want to be able to deal with missing parts, non-isometric deformations, and geometric and topological types of noise. Okay, so there are several ways you can approach the correspondence problem. One may be a little bit naive, but the most straightforward, just learn some local features, right? Usually in computer vision, at least maybe a decade from ago, people worked very hard to construct some axiomatic features, some handcrafted descriptors. So the same effort existed in computer graphics and geometry processing literature. Basically, you can replace these handcrafted descriptors with something that is learned in a task-specific way. And in particular, if we are given a training set of shapes with known correspondence between points, we can basically apply the intrinsic CNN to some geometric information on the manifold, and we can produce a new set of features, and we want that between corresponding points, these features will be similar, and between non-corresponding points, these features will be as dissimilar as possible. Okay, so we'll use the standard Siamese architecture for this purpose. A different approach to modeling correspondence is a labeling problem, and this is particularly good when you consider a specific class of shapes, for example, human shapes. You can choose one of the shapes as your label space, and then basically the correspondence will label each vertex on a query shape as a probability distribution in your label space, as basically denoting the probability of point X corresponding to point Y, right? And if you have the ground truth correspondence, you can actually measure some distance between the ground truth distribution and the distribution that is produced by the network, minimizing the standard cross-entropy or logistic regression function. Okay, and the way that we evaluate the quality of the correspondence is, again, looking at the correspondence that is produced by the network, comparing it to the ground truth, and at each point measuring the distance, the geodesic distance on the reference shape, that basically measures how far we landed from the desired correspondence. Okay, and we can look at the percentage of correspondences that fall within certain geodesic error radius, and basically that's what is called in computer graphics community the Princeton correspondence benchmark. Basically, these curves plot the percentages of correspondences versus the threshold, the error radius, and the higher the curve is, the better. So you can see that, for example, when using an intrinsic architecture like the mixture model network, you get significantly better performance than standard methods that do not use learning, such as blended intrinsic maps. So maybe a different way to visualize it, we can show the point-wise correspondence distortion, basically the deviation from the ground truth at each point. Here you can see what the blended maps produce. So this was one of the state-of-the-art methods in computer graphics that actually doesn't rely on learning. It produces nicely looking correspondence maps, but if you look at the distortion, it can be pretty large. So here it's calibrated in absolute units. 15 centimeters is about the size of your palm, right? So it's pretty big error. This is what we get with geodesic CNN, so it's significantly better. Basically, colder colors closer to white represent smaller errors, but there are still some spurious points where the correspondence error is large. This is what is produced by anisotropic CNN, and this is what is produced by Monet, which produces very nice correspondences. Maybe another way of seeing it is by applying this correspondence to texture mapping. So you can see that the texture mapping is almost perfect. There are almost no noticeable distortions of this texture. So this is another example of some more challenging cases where you have actually both missing parts and topological noise, and you can see still that this framework produces very nicely looking correspondences with small error. Okay, so what is the problem in general of this classification-based approach is that actually doesn't distinguish between a point that deviates significantly from the ground truth or it deviates just slightly. So basically, a correspondence that lands here or lands here, where the green one, of course, is more distant from the ground truth, will be considered the same. Basically, it will be considered as incorrect classification. So a better way is actually to consider the probability distribution itself and use it as a weight to weight the geodesic distance by this probability distribution. So in this way, we can account for what we call the soft correspondence error. Now, the second problem with this approach is that actually we don't impose any structure on the correspondence during the inference time. Of course, during training, we can penalize for correspondences being distant from the ground truth, but nothing guarantees that when we apply our learned model to a new set of data, we obtain that two nearby points will be mapped to two nearby points on the reference shape, on the target manifold. So in computer vision, basically this kind of problems is usually referred to as structured output or a structured prediction. So we want some intrinsic equivalence of structured prediction. And the way of doing it is to resorting to what is called functional maps. So I will not go into details. Basically, the idea is the following. As before, as in the Siamese metric learning, we produce some features at each point of the manifold that now, instead of comparing these features, we'll compute their Fourier coefficients. So basically, we'll project them on the Laplacian eigenbasis on each of the shapes separately. We'll have two different bases. And then, using these Fourier coefficients, we will compute a matrix, basically a linear operator, that translates one set of Fourier coefficients from one basis to another basis, right? Because we know that these bases usually behave differently. So was actually one of the reasons why spectral learning methods do not generalize well across non-isometric domains. So basically, these metrics exactly tells us how to translate one set of coefficients to another one, and it actually has a closed form expression as the pseudo-inverse of this feature vector. So basically, we need here to backpropagate through this pseudo-inverse. Once we computed this spectral representation of the correspondence, we go back to the spatial domain, and basically you can interpret it as a probability distribution. If you take the absolute value and normalize it to sum to 1, then you get basically this interpretation that delta function corresponds to some blob, to some distribution on the target shape. And basically we use these, the probability distribution in our cost function. Okay, and this produces significantly better results than all the previous models. So this is the Faust benchmark on which the performance almost reaches 100%. So this is currently state of the art in this particular type of applications. Okay, so let me show you another type of applications, and this is related to matrix completion and recommender systems. So this will actually involve products of graphs or multiple domains. Okay, and I guess you all know about the Netflix problem. So this is a problem of recommending movies on Netflix. So Netflix has tens of millions of users and probably hundreds of thousands of titles. And the users can give different scores to the movies depending on whether they like them or not. So you end up with a huge matrix that is only very sparsely sampled. Basically, every person, even if he or she spends all their lifetime watching movies on Netflix, probably they will see just a small fraction of what is available. And basically, they want to fill in all the missing elements. And the classical approach is minimization of the rank of the matrix, basically try to fit to the data some low-dimensional structure that explains this data, that is consistent with the observations. Because minimization of the rank is an NP-hard problem, it is usually approximated basically by a convex proxy, what is called the nuclear norm. The problem with this formulation, though, is that it doesn't involve any structure. So if you shuffle the columns and the row of the matrix, you will get the same rank. Or, for example, if one of the columns is entirely missing, then you can fill it in infinitely many ways. So a different approach would be to incorporate some information. It can come actually from the data itself, or it can come from some side information that allows us to define affinity of different users or of different items in the form of a graph. So basically we can think of social network, and you can come up with a model that tells you that friends will usually share their tastes, right? So we can talk about notions of smoothness of this matrix, column-wise or row-wise, with respect to these graphs, right? And you can basically replace one low-dimensional model, basically the low-rank model, you can replace it with a different low-dimensional model that is understood that the rows or the columns of this matrix can be expressed with a small number of Laplacian eigenvectors, right? Basically, it's a low-pass filter, in a sense. So you can do it for using only one graph for the users. You can also use it, a graph for the items. So basically, now you have two graphs on which this matrix lives. And of course, it is possible also to factor the matrix into column and row factors and represent it with smaller number of variables. So I will not go into the details. Basically, these are some standard techniques to address these matrix completion problems. Okay, so basically, if you think of this model where we have this notion of smoothness applied to a matrix, basically it's a low-pass filter, right? And of course, nothing in the world tells us that that's necessarily the best filter. So we somehow, as we've seen in the previous approaches, we want to learn optimal filters that describe our data in the best way. And now the difference from the previous case is that we have actually two graphs, right? And the analogy would be a two-dimensional Fourier transform. So think of how you compute Fourier transform of an image. Usually you would apply Fourier transform to the columns, and you apply the Fourier transform to the rows. And basically this combination of two Fourier transforms gives you a two-dimensional Fourier transform of an image. You can also write it as a Kronecker or tensor product, okay? If you parse your image into, basically if you stack it into column or row stack. So the same thing can be applied in this setting. Instead of basically row-wise and column-wise Fourier transforms, now we have Fourier transforms on the respective graphs of users and items, and the Fourier transforms are, as previously understood, in the sense of projections on the respective Laplacian eigenfunctions. So basically we can define the multi-graph Fourier transform in this way. Basically we multiply our data, the matrix X, by the Laplacian eigenvectors from the left and from the right. And we can define multi-graph spectral convolution exactly as we've seen before, basically as element-wise product in this two-dimensional Fourier domain. Okay, and as before, we don't necessarily need to explicitly compute the eigenvectors of these Laplacians. We can parameterize our filters as polynomial functions of frequencies. Now these will be p-variate polynomials, so they will depend on two frequencies, the eigenvalues of the row Laplacian and the eigenvalues of the column Laplacian. So we have more coefficients now in these polynomials, but the idea is exactly the same. So again, if you think of the spectral transfer functions of such filters, you can think of Fourier transform of an image, and now we have two frequencies, so these filters will be two-dimensional. So overall, basically, this construction of multi-graph CNN allows us to extract spatial features from this matrix, and we can come up with basically with a sequence of updates that change the score matrix based on these features, for example, involving a recurrent neural network. So I will not go into details. You can actually see a poster that will be presented on Tuesday that describes in details this approach. Let me just show you how it works. Basically, this is a synthetic example. We have a matrix that is sparsely sampled. All the blue values are zeros. And basically, this is a learnable diffusion that diffuses these elements and to the missing elements of the matrix. Here you see that the root mean square error is pretty large. The score here ranges from 0 to 5, so this is more or less meaning that the scores are meaningless. So this is our initialization. After 5 instances of these iterations, we get significantly lower root mean square error. This is what happens after 8 instances, and this is what happens after 10 instances, so we get almost perfect reconstruction. So this is, of course, a synthetic example. We don't have any noise, but it just shows that the model works. And these are some real data sets that are typically used in this community of recommender system and matrix completion. And again, we get some good results with these models on these data sets. Okay, so I will now pass the stage to Joan, who will talk about applications in particle physics and chemistry, and we'll conclude this tutorial with some future directions and concluding remarks.
Okay. So hey, so we are going to just conclude this tutorial with just a final batch of applications, and I just wanted to, so let's first discuss about the applications in chemistry. So, in quantum chemistry, there's many areas where this thing could be potentially used, but in particular, the general setup is that for a given molecule, we're interested in predicting a bunch of different things, right? That might be of interest for describing the properties, the macro properties of the molecule, like the energy or the vibrations on or the electron energy gap, for example. And so typically this problem is addressed with something called a density functional theory, which is a complicated and sophisticated technology from quantum mechanics that basically deserved a Nobel Prize. And so the question or the motivation here is to what extent one can define models that are data-driven that somehow provide an alternative to this density functional theory that is perhaps more efficient, like less computationally expensive, and potentially also more precise to some of the problems. And so this is actually an area that kind of sparked and motivated a lot of research in graph neural networks. And so I just wanted here to mention some of the works that addressed this problem and at the same time developed important updates on basically the design and the architecture of these models. So just to mention a few, so there was this first work by David Duvenon and his group, where they used essentially they used a model that was a GNN, like as Arthur described, but where, depending on the degree of every node, you would use maybe a different set of parameters. Then there's a family of works that introduced this idea that also we described at the introduction and that Arthur also mentioned, where a very natural way to enhance and to make these models more powerful is not only to propagate information across the nodes through some fixed adjacency metrics, but also to learn or to modify these adjacency metrics in a data-driven way. And so this was done by this series of papers, and leading to the recent paper by Google Brain, where they coined this name, the neural message passing for chemistry. And all these works, in many of the data sets that they are tested on, they reach what's called the chemical precision, which means that, statistically speaking, the error they make relative to the density functional theory is of the same order as the error that the density functional theory does with respect to the ground truth. So now, basically, this opens the door to maybe the need to develop maybe larger data sets or more precise data sets to maybe verify whether these models can not only match the DFT, but also improve in some respects. And so, so this is for the quantum chemistry, and I just wanted to give you some background. So let me talk to you a little bit more about another setup where this thing is used. Sorry about the picture that is kind of slanted, but so this is supposed to be the LHC, so the Large Hadron Collider in CERN, and in this big experiment, there's in particular one that we care about that is called the ATLAS, which is a detector for that was one of the responsibles of the Higgs boson some years ago. And here we are interested in answering specific questions on like basically particles at the fundamental level. And so that's the kind of picture that we can think of these experiments, is that we have maybe some theory, right? We have a model for fundamental particles, how they interact, and these particles, when there's a collision, they are predicted to behave in a certain way, to produce certain events. And these events, as you might expect, they propagate, right? They create more and more events that make precise modeling, more and more intractable. And so this is the theory, but then the thing that is actually detected by physicists, by experiments, it comes from this complicated machinery. But the idea is that the particles that crash, they travel several different layers of detector, each of them of very different technology, etc. But at the end of the day, the goal is that given some event that corresponds to that can be described as a set of different four momentum particles, x1 to xn, the experiment has designed a simulation that, depending on whether we are to expect a phenomena, for example here the W boson should behave a certain way, and if it's not, it should behave in a different way, right? Like what we call the background signal. And so this problem has already been addressed using deep learning, data-driven models, mostly using two paradigms. One is to think about what the detector sees, trying to map it to an image, by interpolating the input for momenta into the appropriate image on a regular grid. The other approaches are based on exploiting the tree structure of the tree to use like recurrent neural networks models. So here, sorry again, the thing is shifted. So here, what the detector sees is more naturally these four momenta can be embedded, can be seen into like in a native four-dimensional space as a point cloud, right? And so here in this point cloud, what we do is that we construct a graph neural network where the adjacency is learned, and here what we observe is that this model currently is obtaining the best efficiency, the best trade-off between detection and efficiency as previous approaches. And if you are interested and you want to know more about this particular application, there's a talk in the NIPS workshop in machine learning for physical sciences, where is Isaac Enrion, here the student at NYU, is going to explain this thing in more detail. Okay, and so and these are the other directions where these applications of message passing networks to particle physics. These are the sort of questions that currently we are trying to address. So in particular, one of the important limitations of this model is that if you want to learn a priori how every particle talks to every particle, this scales quadratically with the number of particles, which makes it intractable very fast. So one of the important questions here is how to devise mechanisms to scale these things to larger domains. Okay. Yeah, and this is the talk if you want more details about this work. Okay, and now I'll just conclude with a last application where we can apply these models of graph neural networks. So this is what's called the quadratic assignment problem. So it's a very classical problem in operations research and in combinatorial optimization, and it's this goal of trying to match a collection of resources, like a bunch of factories, to a collection of destinations, like maybe locations. And so what you want to try to optimize is a trade-off between how much do I need to communicate between different factories and how far away are the different sites in which these factories can be put, right? And so in mathematical terms, you can formalize this problem as trying to find the best matching between the two graphs that optimizes a kind of I would say like a correlation, or like that you want to try to permute the nodes of one graph such that the permuted graph looks as close as possible to the second graph, okay, as measured by this cost function. So because we are optimizing over the space of permutations, this is not surprisingly a very hard problem to solve. It's actually NP-hard, and you can prove that you cannot approximate it with polynomial time. And it includes the traveling salesman's problem as a particular case. And so typically the way what people try to do is to relax the constraint of permutation matrix into a constraint set that is a bit more tractable. For example, by using a spectral approach, or by using semi-definite programs. So how can we use graph neural networks to address this problem? So for this, we need to generate data, right? If we want to use like a data-driven approach, we have to generate data. So the way this thing we consider to do is to first look at this problem in like specific families of random graphs that capture some of the difficulties of solving this problem. So the way it works is that we sample a graph from like a random graph family, for example, Erdos-Rayni, or like a random regular graph, W1, and then we generate the second adjacency matrix as being a generic, like a random permutation of the first one plus some noise. And the noise is just taken to be Erdos-Rayni. And so, as you can expect, the goal of recovering this permutation is going to depend on the signal-to-noise ratio, right? The amount of noise that we include into the system. So what we are trying to do is we map this quadratic assignment problem into a linear assignment problem by taking the graph G and embedding each of these graphs with a Siamese architecture that is going to produce for every node a bunch of features. And now, once we are in this feature space, we can just solve the linear assignment problem. And so we can do that by essentially unrolling the Singhorn algorithm that what it tries to do is that transforms the gram matrix of the features into a permutation matrix by applying a softmax at every along rows and columns. And so this architecture now can be trained end-to-end on this random graph family. And what we obtain is preliminary but encouraging results. So on the Erdos Rainy model, what we obtain is on the x-axis you have the amount of noise, and on the y-axis you have the accuracy, or how well are you doing at recovering this problem. And so what you can see is that in both cases, in red you have the data-driven model that's basically as good as or much better than the standard ways to relax this problem. But not only that, but at that speed that is very interesting, right? So here, all the operations that we are considering, there's nothing that scales worse than n squared. Okay, so this is encouraging results, and there's a lot of things to understand yet why this thing works well. But as Michael mentioned, some applications to shape correspondence. Shape correspondence is clearly an instance of an assignment problem that is quadratic, right? You want to match basically two manifolds, one to each other. So an obvious thing that we are currently exploring is how to use this architecture for the shape correspondence. And now I want to just briefly mention about some of the other future directions that involve graph neural networks in some form. So one interesting and obvious one is to do generative models, right? So we have seen very successful generative models for images in the last years. So one question is, well, what is the equivalent of a generative model for graphs? So here these are pictures from an anonymous submission from MyClear. Maybe the author is among the audience. It's anonymous, I don't know. So here are some molecules generated by a variation autoencoder, which is trained on by using encoders and decoders being graph neural networks. There's other examples of synthetic synthesis with applications to graphics. So on the first example, you have this problem of inferring a shape from a point cloud that can be partial, using also again ideas from variational autoencoders. And on the bottom, you have an example of temporal prediction under nonlinear dynamics, right? Where here we just throw shapes on the floor, and we ask the model to try to predict the dynamics. And so these are examples and applications that naturally what you would like to do here is to exploit the intrinsic geometry of the object, right? By using the appropriate graph neural networks. So this is just wrapping up the second part. So, and maybe also wrapping up the tutorial. So what we have tried to convey here is that many of the reasons why convolutional neural networks work well, they extend beyond the Euclidean domains, right? So in particular, this idea that you can share parameters across the domain, and you can learn step by step by using local models is a property that not only can be used in general domains, but we have reasons to believe that there are many tasks that capture where this inductive bias is the right one. And so we have seen two different approaches to accomplish or to achieve this good trade-off between locality, weight sharing, and complexity. One of them is using basically the spectral properties of the graph. The other one is directly working on the spatial domain. And as Arthur mentioned, this class of architectures that we define, they are also very related to attention mechanisms that have been so successful, especially in the domain of natural language processing. And so, as I said, one of the things that we still don't know how to do, or that are completely open, is how to scale these models so that they can process maybe systems and domains that have large number of nodes, maybe millions. And we are also interested, and if you have questions about this, we can, of course, very happy to discuss offline, of where can these models be applied. Because once you start having a neural network that can understand well how to process like a set of inputs and learns about how these things should be related to each other, we believe that there are many areas where this thing can be potentially useful. And so with that, let me see if this is the, yeah, so just ending with an advertisement. If you liked this tutorial, there's an upcoming workshop at the IPAM, the Institute of Pure and Applied Mathematics, here in Los Angeles in a couple of months, where we are going to have a week-long sessions around basically methods and applications of these ideas. And yeah, here's some bibliography. Everything is going to be put online. And with that, we just thank you very much for your attention and open for questions now.
So we have plenty of time for questions. If there are questions, please can you line up by the projectors again? And I guess if Max Welling is ready, then we can start already.
Hi, thank you for the wonderful tutorial. So I have a question. So in group convolutional neural networks, they're also driven, it's also generalization of convolutions, and it's also driven by beautiful harmonic analysis. So do you see whether what you presented is maybe a unifying framework, or do you see relations between the two?
Yeah, that's a very good question. So it's true that if you can think about the group as a very nice-looking symmetric manifold, right? It's a manifold that comes with a bonus, right? It comes with operations that are akin to the orientation that Arthur was saying. So I think about the group convolution networks that exploit this group structure as being a kind of a generalization that really stays in this case where you do have orientation, right? And the question is, how do you exploit it? And it's, yeah, and actually this is there are probably examples and domains where if you know that there's this group structure, you should use it. So in a sense, what we presented here is a setup that is a bit weaker because it doesn't exploit this group structure, but on the other hand, it's a bit more general, right? Because you can apply it even if you don't have that group structure, right? So you don't even have that like the manifold at every point. The neighborhoods look very different, right? And so, but and actually would be fascinating and interesting to maybe think about combining the two, right? How could this thing be combined? That's a very good point.
Thank you.
All right, and on the other side.
Thank you so much for your presentation. Just one question with regard to the mixture neural network that you explained earlier. So as far as I understood, the patch operator that you learn has a fixed size, whereas, on graph you can have, different size of neighborhoods. So how does that deal with, that? Because you have a J, the number of kernels that you learn.
Sure. So the size, basically, the size of the page is, in this case, is understood as the number of the weighting functions. The way that, basically, the weighting functions are something that is local. So basically, it's a function defined on the manifold that it has a non-zero, it has support only around the vertex. So basically, this construction can eat neighborhoods with any number of vertices around the vertex. Yeah, so basically, the use of certain number of weighting functions is what defines the dimension of your page, right?
I see. And one, the difference between the traditional convolutional neural network and this type of neural network that you mentioned, you're also trying to learn the patch operator on the top of the filter itself. So does that bring any specific benefit to the table?
Well, so you probably can do the same thing for images. I'm not sure it is of any benefit, probably, again, because in images everything is so well understood and so optimized. But we've seen that basically it gives an advantage because rather than, for example, we don't know exactly what's the size of the page that you want to use. So in this way, basically, when you allow to optimize also for the positions and the orientations of the Gaussian kernels that constitute the weighting functions of the page, basically this way you can also control the size of the page, right? You learn the optimal size. So maybe these ideas could also be used in images. Again, we never tested it.
Thank you.
Thanks so much for the great talk. I have a question about these methods and how they generalize for manifolds with genus greater than 0. Earlier you referred to the deformation correspondence case for genus 0, but I'd love to know more about genus greater than 0.
Sure. So the genus actually, with this definition of convolution, if we're talking about spatial convolution, basically all the operations are local. So there are some subtleties. So for example, if you construct the page using geodesic system of coordinates, basically the radius of the page must be smaller than what is called the injectivity radius of the manifold. So basically the injectivity radius guarantees that this local neighborhood has topology of a disk. But ignoring for a second this thing, it can work. So maybe when you have some topological noise, some points where you have shortcuts, so maybe at this point the construction of the page will not be completely valid, but basically maybe the output of the network will be noisy. But otherwise, it's a local thing, so it works on different topologies. So it doesn't need to be genus 0. Most of our examples that I showed, most of the human shapes, they are genus 0, but some other examples, for example, when you have missing parts or connectivity noise, they have arbitrary genus.
Thanks.
Hi. Had a question about the application. So in the case of the point correspondence from a point cloud to the human body model. So you've shown examples where there's a significant amount of missing data. But have you tried it out with examples where there's some external object in the point cloud? So say, for example, the person is holding a mug or a ball is in front of the person.
So you're talking about the setting of clutter, right? So you not only have missing parts, but also some clutter. So, well, it will be a slightly longer answer. So we showed the application that I showed, the best performing correspondence is the functional map network, basically where the functional maps are incorporated as a differentiable layer in the architecture, and the correspondence is learned end to end. So basically we have a generalization of functional maps to the partial setting that is also capable of dealing with clutter. We still haven't done it, basically we haven't incorporated it in an end-to-end learning system, but it should be rather straightforward and very similar to the functional map network to do it. So probably that will be the answer.
Thank you.
Okay, I'm not sure if there are more questions, but if anyone thinks of any question, I'll ask one just now. I had a question actually from the first half of the talk. You were talking about how to do basically pooling layers for graphs. Now, if things happen in graph neural networks in the same way that they happen in many other types of neural networks, there's going to be a lot of hacking and a lot of, let's say, engineering-driven network design. Are there things that we need to be concerned about, let's say, stability or convergence to something sensible, some sort of sensible function? Like, what are the conditions on pooling that are actually important to make sure you learn something that's going to really be like a general thing?
Sorry. I'm not 100% sure I understand what you mean by stable. So I mean, in general, when we do pooling on a graph, what it means is you have to have some sort of clustering structure, right? You have to have some, and I guess what you're asking is, how can I make sure that the pools are sane? Is this the question you're asking?
Yeah. How can you make sure that when you perform that pooling, it's not that you have a very minor perturbation of your data or some structure of your graph, and then all of a sudden you get a very different pooling structure?
I see. Okay, so in some sense, you cannot guarantee this for most. I mean, this is the problem with hierarchical clustering or clustering in general, right? But there are several things you can do, and one of the kind of most effective, I think, things you can do is what's called cycle spinning in the wavelet or kind of harmonic analysis community, and that's you don't cluster once or you don't pool once. So what we're used to doing in ComNets is we have a grid and we have pools, right? And those pools are defined once and for all. You have one set of pools. What is a saner thing to do in kind of dangerous situations where the structure might, a little wiggle might change the pools, is you recompute a pooling structure 15 times and you average the outputs over those. And this tends to be a very kind of robustifying thing. It's actually done in Euclidean cases as well to deal with edge effects and things like that in wavelet transforms. But
Okay, so then the costs of that are an additional constant 15 times something, but it's not so bad.
It's an average, so that's a thing that can be done fast.
Okay, well, it seems like the questions are done, so let's thank the speakers again.